All right, so welcome everyone. This morning we start with Beatrice Pozzetti, who's going to tell us about the geometry of hyperconvex groups.
Yeah, so thank you very much, Francesco, for the introduction, and thank you all for making it after the conference dinner. I'm really, I know how hard it is to be still here on Thursday, early on Thursday morning. And thanks a lot to the organizers, both for putting together this fantastic conference and for giving me the opportunity to speak here. And like the topic I chose today is some piece of joint work with James Farr and Gabriele Viaggi that I chose because it fits at the interface between two topics that two areas of mathematics in which Misha contributed a lot and contributed a lot of great ideas, and in a sense we're doing some push out of two different directions in Misha's math. So that's why I hope that he likes this kind of results, and that's why I wanted to tell you also about this here. Okay, so what will be hyperconvex subgroups? I want to tell you first roughly what they will be, and then we will get to some definitions later. So to have in mind what this is and what are these two areas of mathematics, these hyperconvex subgroups will be subgroups gamma, finitely generated subgroups gamma of, say, SLTC, or maybe SL3C is already interesting enough for today. So with lots in common with convex or compact subgroup of the isometry group of H3. Isometry group of H3, which is PSL2. So here, D will be for what we do, D will be at least 2. And as we have already seen in Ursula's talk, there is really a distinction between 2 and bigger than 2, because H3 is strictly negatively curved, while here we have like the geometry that these groups will go about to see has a lot of flatness in it that we have to deal with. Okay? And the idea is that the two areas that I want to put together to get some results, with James and Gabriele, are really the hyperbolic geometry of H3 that has the specialty of H3 among all real hyperbolic spaces, is that really here I have some conformal geometry on the boundary, and I'll tell you something about that. So there is quasi-conformal geometry on the boundary that's special of this case here, while here we have some high rank features, and in both these areas Misha contributed a lot. Okay? So, and the rough plan is to tell, our motto is that these groups that I'm going to define you in a bit have lots in common with these better studied groups, and we want to make this precise in some results. Okay? So that's the plan for the talk, the rough plan for the talk, and bear with me and to see more about this. Okay, so what is special for me about this setting here? So if I have a convex compact subgroup of the isometry of H3, this means that this acts on the 3 ball, H3, and has some convex subset on which it acts co-compactly. This means that some drawing of some examples of these settings are groups in quasi-function space, which means that gamma is isomorphic to the fundamental group of the surface and acts on H3, preserving a convex sect and acting co-compactly. This means that the quotient manifold is going to be a hyperbolic structure on surface cross the interval, and the action on H3 will have some orbit maps that accumulate on some Jordan curve at infinity, which will be the limit curve lambda gamma is a set, is some Jordan curve. And other examples are more, if you have, there are lots of different topological type of infinite volume manifolds or open manifolds that support hyperbolic metric, so that this action is convex to compact. And another example to keep in mind is that of cylindrical manifolds in which the limit set is going to be some Sierpinski carpet that we've seen a little bit in Alice talk, so the complement of a set of disks in the boundary of H3, which is CPU. Yeah, so the idea is that you take points, you choose one point in H3, you look at its orbit. Its orbit is going to be discrete because the action is discrete, and accumulates on some fractal set at infinity, which is topologically homeomorphic to the boundary at infinity of the group gamma, but has some interesting geometry that's finer, and it is really a planar subset, a subset of the complex plane, or CPU. And I mean, what makes H3 special among rank 1 symmetric spaces is really that we have really the one-dimensional complex geometry of CP1 that we can use to study, for example, properties of the limit set. And one result that I want to single out here is like the outcome of Patterson-Sullivan theory. That says that metric properties of this fractal set at infinity reflect geometric property of the 3 manifold or the action on H3. So, and the result I want to mention here is that the Hausdorff dimension of the limit set lambda gamma, this is the exponential growth rate of orbits in the symmetric space. So, some version of the constants that Koji was looking at yesterday, but adapted to the geometry of disembedding of the subgroup in H3. So the Hausdorff of the Hausdorff dimension of this limit set of this red set in my drawings up there is the limit as 1 over t logarithm of the number of gamma in gamma, such that the distance between O and gamma O is smaller. Which you can think of as elements that have word length smaller than something. I mean, you count how many orbits you see in a ball, and you expect to see exponentially many, and this is the power to which this exponential growth grows. So exactly the same constant that we've seen in the exponential growth, and these will depend on the specific group that you choose, and this will be reflected in this metric quantity of this fractal at infinity. Okay, so this was the first part of, so this was some brief introduction / reminder of something that has been done in hyperbolic 3 space. And the idea is that we want to understand similar phenomena for actions on manifolds that are not anymore negatively curved, but are non-positively curved now. So that we want to look at subgroup in SLDC, and I want to think of, and this is about gamma, and for the purpose of my talk, gamma in isometry of H3 is convex compact, and lambda gamma in CP1 is its limit set. Okay, so how about SLDC? So SLDC is a group of d by d matrices with complex coefficient and determinant 1. but this is the isometry. I can think of it as the isometry of SLDC mod UD, and this is the symmetric space which is a non-positively curved Riemannian manifold of rank d minus 1, which means i.e. for any pair of points x, y in my symmetric space, x, there exists an isometrically embedded copy of Rd of the Euclidean space of dimension d minus 1 in X, isometrically embedded, containing X and Y. So if I take 2 points, so like the symmetric space is still a ball of dimension, of green dimension that depends on d, and for any 2 points x and y, there is, of course, a geodesic connecting them, but there is always at least one copy of Rd minus 1, so a flat subspace of dimension at least 2 that connects them. And the group acts transitively on this pattern of flats. Outside these flats, the geometry is negatively curved, so there is lots of negative curvature, but there is also lots of zero curvature, lots of flat subspaces. And the group acts transitively on this complicated cat-zero geometry, really cat-zero geometry. And Ursula already mentioned beautiful work of Misha with Leb and Porti on the study of some discrete subgroup of SLDC that are still very hyperbolic in very concrete way. So let me say one more word. Like before I tell you, maybe. They study what they call Uru subgroups of PSLDC, where Uru stands for uniformly regular and undistorted, where undistorted means that they are quasi-isometrically embedded. So the orbit maps which in the case of, in this case of PSL2C, being QI embedding via Miller-Schwarz is the same as being convex or compact. So that's like, this is one condition. But in order to understand higher rank analogs, we need to add this uniformly regular condition, which can be stated as sigma k minus sigma k plus 1 of gamma is more or equal to the norm of gamma times c. So the uniformly regular means that there exists a constant c such that an inequality of this kind works. And I want to tell you what is where if gamma is in SLDC, sigma k is the kth singular value, which is the log of the kth eigenvalues of gamma star gamma. So like gamma is a matrix with complex entry. I can take the transpose conjugate and obtain a Hermitian matrix. These as real eigenvalues, and I can take real positive eigenvalues, and I can take its logs, and this is one measure on how big this element here is. But the way in which you should really understand this condition is understanding a little bit more about this beautiful geometry of symmetric spaces. And here I was telling you that there are d minus 1 dimensional flats, and the group acts transitively on this set of flats. And for any 2 points, there exists one flat containing them. And but the point is that pairs of points mod PSLD are really in bijection with lists S1, SD, such that S1 is bigger or equal than SD, and S1 plus SD is equal to 0. And these are the singular values. So like the pair O gamma O corresponds to the list of sigma 1 up to sigma. So, and I also want that S1 is big. And what is the idea? The idea is that I have this pattern of flats, and I can draw. So like so this is a picture for SL3C. In SL3C, I have a 2-dimensional flat, and I can think of this 2-dimensional flat as a list of 3 numbers. And if a point is inside, it does not have, this is sigma 1 equal to sigma 2, and this is sigma 2 equal to sigma 3. If all these entries are different, then there is a unique flat. While if 2 are the same, then I have lots of flats that branch. And Kapovich-Lev-Porty insight is that to get nice subgroup, you want to have some uniform regularity, meaning that you avoid these directions where there is a lot of flats possible, so that you your vectors determine a unique flat in the symmetric space. Okay. And so this is to say, I was to get back to my story. I told you a bit about some subgroup of the isometry of H3, and I want to tell you something now about some subgroup of the isometry of this symmetric space for varying D. And Kapovich-Lev-Porty have a very general theory about subgroups of Lie groups in this setting. And they studied this uniformly regular undistorted subgroup. And they proved lots of surprising properties of this. So, theorem Kapovich-Lev-Porty in a series of papers, they proved that if gamma is uniformly regular undistorted, so it's not only a QI embedding, but it's also QI embedding going away from these bad directions, then gamma is Gromov hyperbolic. Which is very surprising because it's just a discrete subgroup acting on a non-positively curved space that has lots of zero curvature. So the fact that the group is necessarily Gromov hyperbolic, so doesn't see too much of the flat geometry, is a striking result. And the second property that's going to be important for me later is that gamma is boundary embedded. Namely, that there exists, let me maybe decorate this. There's K euro. Namely, there exists a boundary map, a continuous embedding, when there is an embedding, psi k from the boundary of gamma to the Grassmannian of k subspaces on CD, which is gamma equivalent. And moreover, transverse, meaning that if so let me, before I tell you what transverse means, let me draw a picture. Maybe I'll draw a picture here. So why, I'll tell you what transverse means in a second, but the idea is that if this was my, I call this boundary embedded. So if this was my symmetric space, X, which is SL E C mod some maximal compact subgroup, then I told you that X is like a zero manifold, so it has a boundary at infinity of X. But as opposed to the rank 1 case, this is not homogeneous. Like the action of the isometry group extends, of course, to an action on the boundary. This action is not homogeneous anymore. I have a stratification, and for any k between 1 and d minus 1, the Grassmannian of k-planes of CD is a closed orbit, closed SLTC orbit in the boundary at infinity of X. So I can think of really this as some boundary of the symmetric space. And so what I'm saying here is that if now my balloon here is the Grassmannian, is a compact space, the Grassmannian of k-dimensional subspaces on CD, I have the boundary map, which is going to map the boundary of gamma, the abstract boundary of gamma, as a Gromov hyperbolic group, as some subset that's homeomorphic to the boundary of gamma inside this Grassmannian. So this is playing the role of my red picture in CP1 in the rank 1 case. And I have additional properties, which you can say, which is some sort of strong version of injectivity, which is made out of looking at two different boundary maps at the same time. So if here I denote by x k the image of this boundary map, so like if I have a point x in the abstract boundary, I call xk the corresponding Grassmannian, the corresponding k-dimensional vector subspace of CD. Then the transversality means that x, so that for every x and y distinct in the boundary of gamma, xk is transverse to y d minus k. So k uru means that for this k that sees the Grassmannian of k subspaces, I have some gap in the eigenvalues. If I have some gap in the k singular value, I also have a gap in the d minus k singular value, because the singular values of the inverse are the one with indices opposed. So I have this psi k in the Grassmannian of k subspaces, but I also have xi d minus k in a other Grassmannian of CD, which realizes this abstract Gromov boundary in a different way in some other limit set. But now if I take 2 points x and y distinct in the boundary, then here is a subspace of dimension d minus k, and I can ask for transversality of these subspaces. This is not only saying that, so it's going to be, it is true that psi k is always, these maps are compatible. So this tells me transversality, this tells me injectivity, but it's telling me more, that I also avoid the bigger subspace associated to this. And like I really love their papers. So they have like Kapovich, Lebenport, they have a series of papers studying these subgroups that are by other, I mean, they're also referred to as K, Anosov subgroup. But while the original treatment of Anosov subgroup was very dynamical, their treatment is really geometric group theoretic. They really do coarse geometry of symmetric spaces. They understand very well the coarse geometry of symmetric spaces, and they do really geometric arguments to prove these nice results. Okay, and why I like such a result that like I have some good, like under this condition, I have some good control of the limit set at infinity. I like it because then games like this can be played. And this is indeed something that Kapovich played very nicely with Subadip Day. That again, the metric geometry of this fractal set at infinity reflects the geometry of this orbit. So they prove a Patterson-Sullivan theory result. Here from today. So they Kapovich, but this is Misha's conference, so I'll write Kapovich first. Sorry, Subadev. That if gamma is k Uro, then the Hausdorff dimension of lambda gamma k, so the limit set in the k Grassmannian subspace with respect to some Finster premetric, sorry, let me just write this correctly. Respect some Finster premetric of lambda gamma k. This is equal to the orbit growth rate with respect to some Finster norm. Where, yeah, so this is the orbit. And so let me, that was an F. So this was, so, and the main idea, so one important idea here is that this Finster premetric is rather hard to compute, but it's made so that the action of gamma on the limit set is conformal. Meaning one difficulty of the study of these fractals in the Grassmannian is that the action of SLDC, and in particular of our group, on the Grassmannian is very non-conformal. I have lots of different, like balls are maps to ellipses with very radii. And the study of Hausdorff dimension for non-conformal self-set is very hard. I mean, even in dimension for R2, we have lots of open problems. And what they do is to understand some analog of that beautiful result in higher rank, is they understand that there can be a Finster premetric on the Grassmannian that's made using Busemann functions, for which this action becomes conformal. And then you can read some growth rate of the group using metric properties at infinity.
On the right side, the distance depends on k.
Yeah. Yes. This is a explicit Finsler distance that it depends on k. So like so like I think to me this is an object that I am very much interested in, and as Koji was saying in his talk, orbit growth rates are very difficult objects. They depend very finely on the way in which I measure distances. And in higher rank, I have lots of different measures to measure distances. And like one beauty of this result is to understand some data at infinity that encodes this geometric property of the action. We have, okay, so and this is valid for all k Uru subgroups, so it's a result that's valid in very high generality. They understand really for all semi-simple Lie group what are the right metrics on the space and what are the nice pre-metric at infinity so that such a result works. On the other hand, together with Andres Sambarino and Anna Winard, we were more interesting on the left to understand some more natural notion of Hausdorff dimension. So the Grassmannian is a Riemannian manifold, and so the most natural Hausdorff dimension is the Hausdorff dimension with respect to Riemannian distance. And the question was, does this Hausdorff dimension with respect to Riemannian distance measure some some interesting growth rate in the symmetric space? This is a different problem, and it's a harder problem because the group does not act conformally with respect to Riemannian metric. And this is what led us to introduce this hyperconvex subgroup that are from the title of my talk, which are some much more restricted class with respect to this all general Uru subgroup, for which we can say something about the actual Hausdorff dimension. So let me say definition. So k minus 1, k, d minus k, k minus 1, k plus 1, d minus k, Uru subgroup is hyperconvex. If I have some algebraic inequality, so if x d minus k intersected with this for all x, y, z in the boundary of gamma, so for any triples of distinct points in the boundary of gamma, I have some linear combination of subspace being transverse, meaning I can write it down, it's not. I'll draw an example in a second. And so this is some 3-point transverse, like if I am k minus 1, k plus 1, and d minus k Uru, I have boundary maps in those Grassmannians. So I have lots of linear subspaces, and I can cook up lots of transversality condition out of 3 subspaces. And this condition is saying that, so let's say that, let me take a case d equal 3 and k equal 1. This becomes that x2 intersected with z2 plus y2 intersected in z2 plus nothing is equal to z2. And the picture is that I have, so in CP2, I have, blue, I have a CP1, which is like the projectivity, like to the point z is associated with a 2-dimensional vector subspace, which is a CP1 inside CP2. And what I'm asking is that if I take x2 and I intersect it in one point, and I take y2 and intersect it in one point, these 2 points are distinct. This is some transversality condition that results in saying that if this is the case, I can look at the map I can look at xi z from the boundary of gamma to CP1, which is the projectivization of Z2 that maps x to x2 intersected Z2. And this is going to give me some planar embedding of the limit set of my group. Okay. For this class of groups, which is non-empty and open, so has lots of possible, has lots of subgroups in it, so it's a high-dimensional set of some character varieties. We prove a parallel of the result of Kapovic and Day, which tells us exactly what the Riemannian Hausdorff dimension of the limit set measures. So the theorem that I prove with Andreas Wiener is that if gamma is K hyperconvex, then the Riemannian Hausdorff dimension of lambda K gamma, so this limit set in the K-Grassmannian, is the growth rate H alpha K, where alpha K of O, gamma O is sigma K minus sigma K. And really what this theorem is saying is that for this special class of Uru subgroups, we have a good interpretation of the more natural Hausdorff dimension in the boundary, which is in terms of some measuring of how the group grows in the symmetric space. And this measure is the difference of two singular values, meaning how far I am from the bad subset where I have branching of flats. My alpha sigma K minus sigma K plus 1, this is sigma K minus sigma K plus 1 is smaller than C. And again, like in one beautiful part of Patterson-Sullivan theory in high rank is that if I have these actions on symmetric spaces, I have various different ways of measuring how big an element is, and different growth rates, like the associated growth rates are different, and they reflect different properties both of the action and on the fractal sativity. No? Any questions on this? So this was my, were these hyperconvex subgroups, how we came up with these hyperconvex subgroups. But the motto, which is not here anymore, is really that these hyperconvex subgroups should have lots in common with the convex co-compact subgroup in H, acting on H2. Convex compact subgroup in H3. And this was what, our paper, our project with Gabriel and James was really about making this motto concrete in concrete results. And that's what I want to tell you in the last 20 minutes of this talk, if there are no questions about this. So one example of a result in which they have lots in common is that algebraically they are the same. First result. Published this year, is that if gamma is K hyperconvex, then gamma is virtually a convex co-compact so gamma is a subgroup of SLDC, then gamma is virtually a convex compact subgroup. Of the SL2C, and so it's virtually isomorphic to a convex compact subgroup of PSL2C. Meaning that, so now my so I have many abstract Gromov hyperbolic groups act as isometries of H3 with preserving a convex sublet, but really very, like, many different types, but very restricted. Like these are fundamental groups of, like, open three manifolds. Like it's a big restriction on all possible subgroups. And in this sense, this hyperconvex has something in common to three-dimensional hyperbolic geometry. And like the idea here is that what I one reason behind this is that we know from this construction up here that if gamma is hyperconvex, then its boundary is planar. Like I have this embedding in CP1. But we have seen in Alice's talk that's still open whether groups with planar boundary, this is the Kleiner-Kapovich conjecture, whether groups with planar boundary are really Kleiner groups, like convex or compact subgroups in PSL2C. And like our proof of this theorem is really to understand the geometry of these groups and actions to see that this is not just planar, but it's uniformly quasi-conform. The action on this, we can get an action on this set, which is uniformly quasi-conform. And maybe I'll tell you a few words about this proof, because I think that the one important feature of our result is that we develop lots of hyperbolic three-dimensional tools to study this large class, this class of subgroups in arbitrary D groups.
Yep. Can you explain the general? I mean, this was, for example, E+3.
Right, that's the same. So like the idea is that in general, I get the CP1, which is not really in the Grassmannian anymore, but it's the projectivization of ZD minus K, ZK, sorry, over ZK, sorry, ZK plus 1 over ZK minus 1. And this is really telling you how to give this map. This is telling me that I start from the D minus K map, and this gives me a point in this CP1. This gives me another point in this CP1. And the fact that the span is like that they are transverse to ZK minus 1 is really telling me that the quotient is injective. So this is really doing linear algebra with these subspaces. And we have done this only for SLDC. There should be a general theory for all semi-simple Lie group with one-dimensional root spaces, so like complex semi-simple Lie groups, but we haven't developed that yet. But again, in here, for any point in the boundary, I get the boundary map in some CP1 associated to it. But the problem is that with this, since I chose one point, I lost the action. I mean, gamma acts on the group, but doesn't act here anymore in any natural way. But we can push forward the action on this group here and ask properties of this. Then I have a fractal in CP1 with some abstract action, psi homeomorphism. And the idea is to to get enough compactness to get some regularity of section. But I want to tell you a little bit more on how we do it, because it's going to be useful. Yeah.
And just have K, U, or U, are there higher dimensional examples?
Yeah, so there are, yes. So if you just, so like this, maybe I should have said a few examples, but, so for example, every hyperbolic right angle Coxeter groups, and even every quasi-convex hyperbolic subgroup of right angle Coxeter group admits one U or U representation. So maybe let me write this. Make the difference. So like, facts. So facts that are our theorem, and I forgot like the so this is a theorem, but I forgot to write down all the authors. So that there is Flechel, Duba, Zhu, and I'm not going to write the authors, but if gamma in right angle Coxeter group is hyperbolic, quasi-convex subgroup, then gamma admits one URU realization, and then it admits many, because all of these are open under small deformation, and then easier result is that if gamma is so something that we write in our paper is if gamma in PSL 2C is convex compact, and I look at the irreducible action from SL2C to SLDC, PSLDC, the reducible representation, then any small deformation of iota d of gamma is K hyperconvex for all K, and many other discrepancies. Generically, this deformation of the discretance. So this gives you a little bit the difference between just asking URU and KURU representation. Here, the abstract type of the group is very broad. Like lots and lots of groups from geometric, lots and lots of hyperbolic groups are quasi-convex subgroups of right-angle Coxeter groups. We've seen this already. And then we have many families of just one URU representation. These groups here are algebraically much more restricted, because our theorem says that they are subgroups, literally subgroups of PSLDC. On the other hand, there are many more K hyperconvex subgroup than convex or compact subgroup of PSL2C, because whenever I start from one, I can deform it to make it Zariski dense, so to see some of the higher rank geometry. Okay? So let me give you and this is something that we observe in our paper. But so let me give you one idea. Is that the action? So the idea of the proof of idea for theorem A is that the action of gamma on the fractal set psi t of the boundary of gamma is uniformly quasi-conformal. So this is a subset of CP1. And thus gamma is Klein, virtually Klein group. And in order to prove this uniform quasi-conformality, so for this, we set up a foliated Kleinian theory, meaning that we consider a bundle over the boundary of gamma where the fiber over any point is the projectivization of T2, say in this example. So this is a bundle over the boundary of gamma where over each point we have a marked limit set. And these vary continuously. And understanding, like the gamma now acts on this boundary moving with a co-cycle that is conformal, because it maps the fiber over T to the fiber over gamma T in a conformal way. And the action on this bundle has nice enough co-compactness that we can assume, we can transfer results from a single sphere, because these spheres are dense enough. And I wish I had more time to say this, to explain a bit more about this, but I've been going much slower than I thought. But maybe just let me say corollary of this result is that in our assumption, the Hausdorff with respect to Riemannian metric of psi of lambda d minus k of gamma is strictly smaller than 2 unless gamma is pi 1 of the compact free manifold, unless boundary of gamma is a sphere. So, okay, should not have to erase that, but so I have erased my result, unfortunately. But our so this was the result that we had with W is if it's K hyperconvex, then the Hausdorff with respect to the Riemannian is H of K root, and developing this foliated quasi-function theory, we obtain that this is like while this fractal lives in a very big dimensional Riemannian manifold, we can strictly bound this Hausdorff dimension by 2. So it's a small group, and this action, while seeing a lot of the geometry, is still very confined in being Kleinian in some sense. And another result that we prove is the other bound. The rigidity of the other bound. Another result that we prove with Gabriel and James is that if gamma is K hyperconvex, then gamma is absolutely isomorphic to the fundamental group of the surface. So it's really quasi-function theory here. Then, of course, this limit set is homeomorphic to the circle, so it has Hausdorff dimension at least 1. But we know that the Hausdorff dimension of the limit set K of gamma is bigger than 1 unless gamma is contained in PSL. And so we prove so it's bigger equal than 1 and it's strictly bigger if, unless I was in the real group. In which case is a C1 curve. Lambda gamma is so as soon as you deform outside the analog of a H2, you get a strictly bigger Hausdorff dimension, so you get a strictly really fractal behavior. And let me tell you one ingredient in this proof. Again, here we really do foliated quasi-function theory as in this bundle setting, but an ingredient is the development of a Alfors-Beers map So like we've seen in Shinpei's talk, the Beers simultaneous uniformization, and we do a version of this Beers simultaneous uniformization in this foliated setting, but our Alfors-Beers map is going to be a holomorphic map with values in the Teichmuller space. Of Riemann surface lamination. In case that, to explain you in one word in my last minute what this is, if gamma was the fundamental group of a surface, I would really get a circle down here, and I would have a circle of CP1 with continuously varying C1 curves. These split into two disks, holomorphic disks, and we can uniformize them continuously to get some holomorphic structure on the unit tangent bundle of a surface. And this is what these Riemann surface laminations are. This is a foliated version of Teichmuller. So my time is up, and I'll stop here, and thank you for your attention.
Question?
I mean, the hyperconvex was asking for it to be k minus 1, k, and k plus 1.
Yeah.
And somehow, I mean, it seems that the PSL2 comes from the fact that it's k plus 1.
Right.
And the fact that it's, and then convex compact is the fact that you have the k in the middle, which showed that, I guess it's related to being one convex compact in PSL2.
Right, that's correct. Yeah.
So do you think that there's a general thing you can just say, if we put three of them, let's say, in some...
Yeah, so like the big advantage of doing k plus 1 and k minus 1 is that you have a one-dimensional CP1 on which the action becomes conformal. And so this becomes really a foliated PSL2C theory, because PSL2 is what acts on this disk. We have developed also analogs in which we take different combinations and different requirements, and but then you get a foliated lower rank version in which, like, if you take two different combinations of flags, the quotient is naturally a flag for some other group, and then we can relate the higher rank geometry, the geometry in PSLDC, with the geometry in the smaller group. Like, for example, like one instance of this is with theta positive representation, in which the quotient is maybe a symmetric space over Hermitian, like it's the isometry group of symmetric space over Hermitian type, which has some SL2R behavior, and you can do some foliated version that way. And I think that there is much more to explore. And like both in just this version of client theory, is just at the beginning, and in looking at more general transversality properties. And like what is key here is really that I'm looking at transversality. It's not there anymore, but I'm looking at transversality of triples of points where I get enough co-compactness. Otherwise, everything becomes much more complicated.
More questions?
Do you get like a pairs embedding into the vector space?
So yeah, that's what I was saying there. So we get an Halford's Bears map, which is going to be a holomorphic map from the character variety of this realization into these two copies of this infinite dimensional technical space. And we also prove a Bear simultaneous uniformization in the sense that for any two Riemann surface laminations, we get a CP1 bundle that uniformizes them simultaneously. But it's very hard to say which pairs in this infinite dimensional space come from these character varieties.
So if you fix one, like the image is
The Bear slides, I mean, it's very hard to say if this Bear slides is going to intersect the character variety in more than that specific point. And I would probably expect not. So like we have the point that we have the Bear simultaneous uniformization on this space of CP1 of marked CP1 bundles, and there you have the we develop a lot of quasi-function theory for these objects. But then this is an infinite dimensional space in which the character variety sits in some holomorphic way. There is a holomorphic embedding of the character variety in here, but what are the intersection with these Bear slices is very hard, and I think it's just one point unless you are in PSL2C character. We can talk more about this.
Yeah. All right, if there are no more questions, we can take the again.